again, thanks for joining us. And as we said, we're going to try and present a few topics from the AIM-1 group that kind of give you a flavor for what we're trying to do. And I wanted to start off with a little bit of an introduction and a background that many of you know, but I think it's important that we kind of think through what we're trying to do in PINEMAP and keep in front of us what our objectives are. A lot of us are now getting pretty deeply into our own work, and sometimes you kind of get a little bit too focused on, or you get extra focused on what you're doing, and you need to step back and say, well, how does this fit in with the overall project? So, so what we're going to do is try and do a spell check, I see, to spell introduction right, but what I'm going to do is talk a little bit about what we're doing, and then Rod Will's going to talk about the Tier 3 installation, which is our rainfall manipulation study. And then Eric Ward will talk about the water use and sap flow work that we're doing to estimate evapotranspiration rates. And then Jason Vogel will talk about the work we're doing on soil respiration in order to try and estimate net ecosystem productivity. And those are just a few of the topics that AIM-1's working on. So again, everyone should recognize, the scope is really the entire range of loblolly pine that we're working with, from essentially Maryland, Delaware, all the way to Texas and Florida, which is a pretty broad area that we're trying to deal with and understand climate change in that area. And if we step back and think again what our overall generic goals are, is to create, synthesize, and disseminate knowledge that's going to enable landowners to adapt to climate change, if you will. And so how do we understand forest productivity in the context of perhaps mitigating changes in atmospheric CO2? Can we sequester more carbon? A major goal is our understanding of water use and nitrogen use efficiency in forests. And then we want to develop adaptive management techniques that allow us to create forests that are more resilient in the face of any of the climate change that goes on, that might occur, whether it's changes in temperature, rainfall, drought, those sort of things. And again, there are some very specific outcomes of the program that NEFA wanted that were quantified, and so we are expected to develop a system whereby we could reduce the use of energy, nitrogen, fertilizer, and water by 10%. And we need to figure out a way to increase carbon sequestration 15% under the developing these resilient forest systems. And there's a deadline on that, 2030, which fortunately is beyond the life of the grant, but still something we need to keep our focus on. And again, to do that, we have the adaptation, mitigation, and education extension roles within PINEMAP, which is, again, why this is a coordinated agricultural project, because it includes all of those. And again, we really all need to take all three of those aspects seriously. The education extension is integral to this, and we would not have gotten the grant had we not had a very competitive and very strong program in that. And just to put a plug in, many of you are working with Martha Monroe and those folks to do the PLT modules and stuff, and there's a pretty impressive amount of work that's gone into developing these new PLT modules, and that's key to this project. So we all need to participate in that. And again, to do this whole thing, we got more than 50 co-PIs, 12 institutions all over the place, and all of you are part of that network with it. And so, the whole project's around 6 aims, and we're going to talk today about AIM-1, which is really focused on developing the monitoring network that's needed to provide the information that fits into some of the other aims, AIM 2, 3, 4, 5, and 6. And so that's really what we're going to try and talk about today is what is AIM-1 doing to fit in that context. And if you look at the overall milestones of the overall PINEMAP project that are listed here, the first three that I've tried to put in bold really is where AIM 1 fits most closely in. You know, in terms of this existing network of monitoring network that we can use to understand and measure the fluxes of carbon, nitrogen, water in the systems, and most importantly, to try and figure out a standardized methodology for measuring those with it, and so that we can see how they interact with climate change. And that will give us this baseline, if you will, of carbon and nitrogen and water use in the system, and then how our future management practices might be changed or adapted to accomplish the original objectives, which are, as we said, you know, reduction in nitrogen fertilizer use, more water efficiency, more carbon sequestration in the forests. And then this all does flow through into other projects. And kind of taken this graph that Tim had done before and made a little bit of a change in terms of showing how we fit in with the mitigation, adaptation, and kind of extension roles. And you have all the arrows between the green boxes and the blue boxes showing how they're all interrelated, as they must be in this project. In another context, though, I think when we think of AIM 1, the arrows on the bottom that I've added to this kind of give us a flavor of how we're fitting in that our real goal is to develop this monitoring network, and the main user of that specific information will likely be AIM 2, the modeling group. And there'll be then the models that we develop through this PINEMAP will be useful in terms of helping other aims accomplish their objectives. And so it sort of is a little bit of a sequential process, I think, at least in how I think of it sometimes, and where we're going to fit in with that. And of course, other of the aims are also feeding back into the modeling group, the policy group, the education group. As we develop DSSs and those sort of things, all have to fit both ways. So maybe those arrows really should have double headers on them, you know, going both directions with it. And another way to think of that is this graph that's been used before as well, is to show how it all sort of fits together with it, in that we have the green box on the left, which is our monitoring network data, as well as our remote sensing data and the climate scenarios, will feed into kind of modeling efforts at various scales, from the stand to the watershed to the region that the modeling group is working with, which then will provide the input, if you will, or the ability for policies and managers, policymakers, managers, to understand climate change and how we might be able to mitigate and adapt ultimately to accomplish the objectives that we had listed. And so AIM 1, what we're focusing on is this three-tiered monitoring network that we've established to quantify the carbon, water, and nutrient storages and fluxes in loblolly pine systems. And the way we've done this is establish three different tiers of data and installations that we'll be working with. The Tier 1 sites, those are the sites that have been established already by all the existing co-ops that we're working with. And they represent primarily what we might think of as archival. They're studies that have been in the ground. Many of them provide data, but they may not actually physically exist anymore, but the data is still useful in a growth and yield context and in that process. And there's a large number of these plots which will help us characterize, you know, the variation in climate and geographic effects on productivity, help us validate the models that we have, and hopefully improve the existing models that are there, ranging from the traditional growth and yield models that we're using up through process models like 3PG and the WASI and CASA models that we're looking at for water and carbon. The Tier 2 installations, excuse me, represent the sites that are active research trials right now where we can collect more data. And so this is sites where we're trying to look at carbon sequestration, so how much carbon is being sequestered, what are the respiration rates from the soil. And so these are sites that can go, sorry, locations where we actually are collecting additional data and trying to understand how that fits in. And then the final thing we have are our Tier 3 installations, which are new studies that have gone in to look at how we can manipulate climate, primarily looking at reducing the amount of water available in the system and what that might mean. So that's a quick and very broad overview to both PINEMAP and AIM-1, but I think I wanted to kind of set the stage and now let Rod tell you specifically about what we're trying to do on the Tier 3 installations and how they're being set up and what they're being used for. So with that, I'll let Rob take over.
All right, thanks, Tom. Our goal with the installation of the Tier 3 locations was to capture a range of productivity and climate across the southeastern U.S. And this slide shows the approximate locations of the Tier 3 sites. Up in Virginia, that's pretty close to where it is. The Georgia site, I think, is a little bit further to the east, but more middle Georgia. The Florida site, I think, is a little bit further west in North Florida. And the Oklahoma site is actually a little bit to the northwest and just outside the natural range of loblolly pine. Okay. We did have some constraints when we chose our stands. We wanted stands that were near crown closure and that had not had previous fertilization. We specifically wanted to get an orchard mix of genetics that were appropriate for the region. The reason for this is to expand our inference beyond just a family or two. That resulted in some variation in planting year. For instance, the stand ages range from 2003 planting date to 2008 in Oklahoma. And that does result in differences in tree size and the extent of crown closure, which you'll see as I go through some photographs. The treatments were a factorial combination of rainfall reduction and fertilization, and of 4 at each site, so there were 16 plots at each location. Gross plot size about 0.4 acres, and the measurement plot size is approximately 0.1 acres. The fertilizer was applied this spring, and we put down 200 pounds of N, 25 pounds of P, and 50 pounds of K. We also put down a full suite of micronutrients applied at a rate of 1 pound of boron per acre. And here's a picture from Virginia showing the application of the fertilizer. Luckily, we had the forethought to spread the fertilizer before putting the covers on the excluders. The other treatment was the water reduction. Our goal was to reduce water through fall by 30%, and we tried to avoid banding wet and dry areas of the soil. To do that, we tried to minimize the width of the excluder, so we actually deployed a split excluder scheme within rows, and we also tried to raise the excluders as high as we could to hopefully reduce the direct rain shadow effect under excluders. And of course, the excess water is being moved off the plots and away from other plots, either through piping or ramps. Here's a completed excluder at the Georgia site. They work very well. Worried at one point about water ponding or pooling in those, but it's really not been a big problem. One unintended consequence is they act really well as litter traps. So we found that we need to go out on occasion and redistribute the litter from the troughs to underneath the troughs. Here's an overview from Google Earth of the Oklahoma site. And it's a recent picture because you can actually see the excluders from space, from satellite. Those little white squares are the excluder plots. And there's 8 of those, and there'd be 8 others that are the non-excluder plots interspersed throughout that site. And so kind of interesting when you can show folks that their hard work installing these is actually seen from space. And then here's a close-up of 2 excluder plots. And, you can see the extent and the hard work that went into putting those excluders out. Here's an overview, a panoramic picture from the Oklahoma site. And there's an excluder in progress being built, and you can see how big the trees are relative to the excluders. Okay, here's an overview of the Virginia site. This is Appomattox State Forest, I believe. And here's a picture from the Virginia site, and the trees are obviously older and a fair amount larger. And here you can see the water being piped off the plots to other locations. An overview from the Georgia site, and a photograph of the Georgia site, and the tree sizes here are in between those at Oklahoma and Virginia. And lastly, an overview of the Florida site. And the trees at the Florida site are the largest of all. A little bit older in age, but also probably higher productivity than the Virginia site as a comparison. So the current status, all the sites have been installed as of last summer. It was an enormous effort that took a lot of people's hard work. And we're happy with the way they're functioning, and we look forward to continuing to gather some, I think, important data from these sites. I guess with that, we are gathering quite a bit of data, data related to productivity, carbon cycling, leaf area, light interception, nutrient status, water use using sap flux methods, which Eric will talk about, leaf level gas exchange at some sites, and then also soil CO2 efflux as it relates to NEP, which Jason will be talking about later in this webinar. A couple interesting things. Disease and insect seem to be, might be a problem as we go forward, as we continue to stress these trees with the rainfall reduction. At the Georgia site, there was some individual tree mortality that may have been related to rust, and then with a secondary insect infestation. So it's something we'll have to keep a close eye on. And then also something unsurprising, or surprising to me at least, was that we've had issues with snow at both the Oklahoma and the Virginia site. At Oklahoma, we had a Christmas Day snowstorm of about 8 inches. Then it didn't quite melt, and then it rained some more on top of that and froze. And we actually had some of the excluders drop down. And there's a picture of what that looked like after that snowstorm. And luckily, no excluders were broken. We just lifted them back up and reattached them to the T-posts, and the trees were fine. But it was one of those unintended consequences of putting out the excluders. With that, I'll turn it over to Eric to talk about the sap flux study, and that's probably one of the bigger efforts that we're undertaking at all 4 sites to get a really good handle on tree water use.
Okay, thanks, Rod. So I'm Eric Ward at North Carolina State University, and I'll be talking about our measurements of sap flux density at Tier 3 sites. For those of you unfamiliar with the measurement method, sap flux sensors consist of a set of 2 hypodermic needles, each with a thermocouple inside of them. These are placed in the active sapwood of the tree. The upper sensor has a heating element wrapped around it. This applies heat and creates a constant temperature difference between the 2 sensors. All right, so when water flows up the tree, then the temperature differential between the 2 sensors decreases, giving us an idea of how much water is flowing up the tree. So at the Tier 3 sites, we have 16 plots, as Rod pointed out, at each site. We have 5 sensors per plot implanted in the outer sap trees. I'll note that these sensors, because of heating, require the most power of any of the sensors at our sites. Therefore, 5 per plot is about as much as we can manage on solar power. Now, to give you an idea what these data look like, we get measurements at each tree of the sap flux every half hour. You can see the diurnal cycles over several days here. These measurements are, as I pointed out, in the outer 20 millimeters of sapwood, just below the cambium, at breast height in the tree. So this represents the flux density across the cross-sectional area of sapwood, here denoted A sub S, which is supplying the canopy of pine trees with a leaf area denoted A sub L. For those of you who haven't done tree physiology in a while, you'll remember that the sapwood just below the cambium is the youngest sapwood, and therefore expected to have the highest flow rates. Outside of this is bark and the phloem. Inside of the sapwood is heartwood, though most of our trees are young enough that there is little to no heartwood formation one would expect. So we have sap flux density in the outer sapwood of 5 trees in each plot. What are the ultimate quantities of interest to us, and how do we get from our data to those quantities? One thing we would like to know is the total transpiration of each plot. This is because we expect this to be the most obvious response to reducing the amount of water going into the trout plots. Also, fertilization can have effects on tree leaf area, and therefore might affect transpiration as well. To scale the transpiration from the sap flux, therefore, we need estimate of the total sapwood area in each plot, as well as the ratio of the mean sap flux across all the sapwood area to that in the outer sapwood that we're measuring. Another quantity of interest to us would be the stomatal conductance of the canopy. Again, for those of you who haven't done tree physiology or plant physiology in a while, the stomatal openings are where water leaves the leaves of the tree, and where carbon dioxide enters the leaves of the tree. Therefore, we expect that stomatal conductance wouldn't have effect just on water transport, but also on photosynthesis. Stomatal conductance, therefore, especially if it's reduced in the drought plots, could be an approximate explanation for decreased growth in those plots. Also, some of the models used by AIM2, such as 3PG, include stomatal response functions. So if we can get a better handle on what those look like at our sites, we might be able to improve those models. For stomatal conductance, then, we need estimates of plot leaf area, as well as some micrometeorological data, which we're collecting at a central tower of each site. Okay, so as I said, to estimate transpiration, we need plot sapwood area. This primarily means getting estimates of bark thickness for our trees, since we have DBH measurements in each plot. We also need an estimate of the ratio of the mean sap flux across all the sapwood area to the outer sap flux which we are measuring. Since we're not doing that for this site, we need to find other sites at which this has been done for low-poly pine. One example would be the Duke Free Air Carbon Dioxide Enrichment Study, which completed last year. And this ratio could be estimated from 11 years of data. And here I show the ratio over those 11 years for each 4-month period. As you can see, it decreases as trees get larger, which we would expect, since a greater amount of the sapwood area is composed of older sapwood as the tree gets larger. We also see that major droughts and hurricanes and an ice storm in 2002 all affected this ratio to some degree, some more than others. But we can see that often in droughts this ratio would decrease, and storms are likely to damage the canopy, therefore decreasing the amount of water and perhaps preventing the recovery of this ratio. I expect at some point those of us involved will have a lengthy discussion of exactly what ratio we should be using at each site. Okay, so once we have the transpiration, how do we go to conductance? Well, just to remind you, in reality, each tree has its own sapwood area and its own leaf area, and these are connected, and they aren't connected between trees. However, when we model this process, we simply look at the canopy as one giant leaf, and the sapwood area as one giant trunk, if you will. Everything's pooled. We don't differentiate different trees. Okay, so how do we calculate small conductance? Small conductance is roughly equal to the mean sap flux across all the sapwood area, multiplied by that sapwood area, divided by the leaf area of the plot, divided by the driving force for evaporation, represented by BPD, then multiplied by some physical constants with weak temperature dependent. Once we have small conductance, what might we be interested in? Well, one thing we're interested in is the response of small conductance to environmental drivers. For example, as vapor pressure deficit increases, therefore increasing the rate of evaporation, small conductance is often downregulated to prevent the trees from using water faster than they can afford to. As light increases, small conductance generally increases since CO2 is needed inside the leaves for photosynthesis. And at low soil moistures, we often see a steep decrease in small conductance as the tree starts restricting its water use so that demand does not outstrip its ability to take water up from the soil. Now, of course, in reality, data are messy. So what I showed you before was sap flux data for a few days, which the sensor was working just perfectly. In reality, sensor over a year looks more like the upper panel. And here we have both short-term gaps and longer-term gaps that might be the result of either power problems at the site or sensor failure. So a question that comes up is, how does one account for this non-random missing data? And especially when we have such a small number of sensors per plot, the loss of one sensor could shift the mean measured in the plot significantly. So we have to do something about sensor-to-sensor differences. Finally, how do we fit small conductance responses to multiple drivers that are all varying in the environment simultaneously? The general approach I've used in the past to address this problem is a hierarchical Bayesian state space model describing stomatal conductance as inferred from the sap flux measurements. We obviously don't have the time for the details on any of this today, but in general, there are kind of three levels you'd want to think about. One is the data which we are collecting at the site. One is the process in which we are interested, in this case, stomatal conductance every half hour. And finally, the parameters we need to estimate to describe that process in terms of the data. Now, this is an explicitly temporal model, so that stomatal conductance at each half hour depends on the stomatal conductance of the previous half hour. We include the environmental measurements we are taking, including the soil moisture probes, which are a wireless network, and the sensors in each plot, both below and between benches in the trout plot. Measurements on the leaf area from diffuse light measurements and litter fall, and sapwood area from TBH. And what we're interested in is the parameters of what's often termed a Jarvis-type stomatal conductance model, which is a multiplicative function describing empirical responses of stomatal conductance to different environmental drivers. This model has error both at the process level and at the level of the sap flux data itself, and includes a random effects model to account for sensor differences. Some sensors always tend to read high, some always tend to read low, and so we need to account for that when a sensor has missing data. This structure can accommodate missing data, and with the simple result of our confidence intervals get worse when we have less data. I think that's about all the detail I can cover on that for today. If any of you are interested, email me and we can talk about it more. Otherwise, I will pass on the microphone to the next speaker. Thanks.
All right, so I'm going to get to the point of discussing why we measure heterotrophic respiration. But before I do that, I just want to go over some concepts and terminology in carbon cycling research that I believe are important for us all to understand. So I know a lot of you out there do understand these things, but we still oftentimes get confused when we discuss them. So as an ecologist or a forester, when we walk out into the forest, we see trees and we see soil with black stuff in it. And we know that as organic matter. And we know that we want to understand how much organic matter is out there. So how we describe that is a function of both the temporal scale and the spatial scale that we're interested in. And as a result of that, the things that we measure in our description of ecosystem carbon gain or loss changes somewhat. So when we talk about carbon loss or carbon gain, we are most often talking about net ecosystem production, which is a term that was defined by Whittle and Whitaker in 1968. And it's most often understood as the difference between ecosystem level photosynthetic gain, gross primary production, plant photosynthesis, and ecosystem carbon loss, plant, animal, and microbial respiration, or ecosystem respiration in the aggregate. Now, in their paper, they actually had another definition which they discussed, and that was the net rate of carbon accumulation in ecosystems. And it's come to the point where ecologists have decided that we have to describe these two things as different entities. So this is the first definition of Whittle and Whitaker. NEP equals GPP minus ER, and GPP is your gross photosynthesis, and ER has an autotrophic respiration component, and it has a heterotrophic respiration component. And both of these then contribute to ecosystem respiration, and all of these processes, of course, are carbon CO2 exchange processes. And this definition is most interested in CO2 exchange, or most relevant to CO2 exchange. Now, the second definition of from 1968 was basically trying to describe the changes in carbon accumulation over an ecosystem's age. So over on the left-hand side, we have an ecosystem right after some disturbance, a harvest, a fire, etc. And heterotrophic respiration is driving carbon loss. And over time, plant growth will take up more and more carbon, and you'll cross the 0 point, and the ecosystem will go in a positive carbon balance. And at any one point in time along this graph right here, the dominant fluxes are photosynthesis and respiration. But as you integrate more and more time into this ecosystem, other fluxes become more important. So down here we have NEP, the first definition, but then we also have other fluxes like methane, DOC, DIC, volatile organic carbon, and particulate matter, primarily from fires or perhaps flooding, either as an input or output term. And when you consider hundreds to millions of years, these fluxes are very important and will ultimately determine how much carbon is stored in any ecosystem. If you look at a plot of ground on the landscape and calculate all the plant growth that has gone on there over 1,000 years, only about 0.5% of the carbon is stored in that ecosystem at the end of that 1,000 years. So all of these other fluxes are incredibly important, and they're also important to atmospheric chemistry. So understanding them over long time scales is critical. I'm going to show you a graph here in a little bit that has the term net ecosystem exchange, or NEE. And net ecosystem exchange is an atmospheric chemist's way of describing carbon exchange between the atmosphere and an ecosystem, but their perspective is the atmosphere, and so they usually use NEE in their description, and it's a negative sign or a different sign relative to NEP, the opposite sign of NEP. So this is a graph from Terry Chapin's paper, and it shows all the fluxes we were talking about, the smaller fluxes, and it shows GPP and the two parts of respiration, ecosystem respiration, which are autotrophic respiration and heterotrophic respiration, shown down here. And, well, we're missing something up here, but, well, I'll ignore that. Well, no, I'll describe what I wanted to say up here. An important thing to remember when you're talking about net ecosystem production or net ecosystem carbon balance is that for forests that have harvested products taken off of them, the loss of products is at the ecosystem level. The plot of ground that you're talking about is a negative. So, you know, very often there's confusion in the literature when people start talking about harvesting is a negative effect on carbon balance. But when you consider the regional scale or the global scale, that carbon is going into landfills and into trees, and so it has a positive balance, and that just requires a different level of ecosystem scale to consider. And it's an important thing to keep in mind, because we do, of course, have a group that's doing life cycle analysis and trying to understand how that exported carbon will affect regional carbon balance. So just contrasting NEP from NECB, at any one point in time, GPP is the overwhelming effect on an ecosystem respiration, having an overwhelming effect on this change in carbon per unit time. But as we go over the entire ecosystem's age, thousands to millions of years, then these other factors, and here I have included a term for forest products, start to become important. Alright, so now we're going to get to heterotrophic respiration. Why are we measuring it? So we're not actually estimating GPP in PINEMAP. It's a very difficult thing to estimate. In fact, we can't really directly measure it using any methodology. But what we can do is measure NPP, or plant growth. This is something that foresters and ecologists are gotten quite good at. And we can use the definition of that, or the reality of it, which is the difference between gross photosynthesis and autotrophic respiration, to insert that definition into the net ecosystem production equation. And then we also take into account that ecosystem respiration is both autotrophic and heterotrophic respiration, and we insert that into our NEP equation and cancel out the two autotrophic respirations. And we have a very simple and new definition for, not completely new, but alternate definition for net ecosystem production, using one term that we're very good at measuring and one term that I'm going to discuss here in a little bit. An important point is that, and I want to make, is that most heterotrophic respiration comes from the microbial decomposition of organic matter, not from giraffes or animals generally. In a few cases, if you have a severe insect outbreak, a gypsy moth type event, then you can have a significant heterotrophic respiration coming from insects, and large animals in the Serengeti, of course, eat a lot of plant growth. But in forests, especially pine forests, animals are not considered important. Okay, so this picture again, NPP now is our primary input to the ecosystem, and PINEMAP and the cooperatives are measuring that process through repeated measures of tree diameter and using allometry to estimate tree size as a function of tree diameter. Over here on the right, we see two fluxes out, heterotrophic respiration and root respiration. And it would be a perfect world if we could easily separate these two things, but unfortunately we can't, and what we effectively do is measure the two of them together as soil CO2 efflux, or soil, what we oftentimes known as soil respiration. Now there are many ways to try to separate RR from RH, but in PINEMAP what we decided to do is install barriers that do not allow root growth into an area of soil, and we measure using infrared gas analyzers the amount of heterotrophic respiration coming out of this secluded area, and we also measure it in areas where there is not a barrier placed. And by doing those two things at the same time, we can get another important term, which is, of course, the root respiration. And rather than using that and net ecosystem production, we can use that to try to understand how plants might change their allocation into our different treatments, whatever they might be, fertilization, weed control, or the rainout exposures. So just to sort of review what we're about in Aim 1 for PINEMAP, we are taking the approach of estimating for many, many different forests, up to at least 28, the difference between NPP and heterotrophic respiration, and using that to estimate NEP. And then that information will go into our modeling group's efforts to extrapolate to the many other forests that we're measuring just for growth. And of course, the nice thing about this is that we're also getting an estimate of root respiration that then can be used to test our assumptions about plant carbon allocation. So I didn't go into much in the detail of how we exactly measure heterotrophic respiration. Anyone is curious, I can recommend many papers. With that, that's all I have.
Thanks, Jason, Eric, Rod, and Tom. Are there any questions? You can either speak up with your microphone, or feel free to write them in the box and I'll read them off.
There's a question about the sunlight from the excluders, and that's something we were concerned about, and the way we're going about minimizing that effect is by the plastic we chose to cover the excluders with is a clear plastic, which allows, I believe, like 90% of light through the plastic itself. But it doesn't get around the fact that it will be reduced either through some of the plastic getting dirty and so forth, but then also the structures themselves. But there's really no way beyond doing that we could attempt to take care of that without building a second set of excluders on the non-excluded areas and putting plastic with holes on it, which we ended up deciding it was not feasible given the cost and the effort to do that. So the short of it is that yes, it could be an issue, but we did the best we could, and we hope it's not going to have a big effect.
I can maybe address the database question. So yes, these will all be stored on Terra C in the short term. We are hosting many of them on the servers here at NC State. In the long term, they are going to Terra C. ASCO's website has many of the data sets that are coming in pretty much real time. They get downloaded every night. So if you are a collaborator that wants to access some of that data, you can contact me and I can help facilitate that. But yes, they will be eventually available on TerraState.
I think there's one more question about obtaining the PowerPoint presentation, and as long as there's permission, I can pass that on to you. So feel free to send me an email. I'll type my email address in here. Are there any additional questions from the group? Okay, well, I want to thank everybody for coming out, and once again, I'm just going to make my plug for the internal webinar series and encourage people to sign up to present. We're pretty open from here on out, and like I said, it could be a good chance for you to practice a talk you're doing. It's on PINEMAP for some other audience. You could flesh out some ideas here. You could co-present with somebody if you want to share the spotlight. We're really open. I think it's a good way to keep everyone up to date on what's going on in PINEMAP since it's so complex. But all right, thanks everybody again for presenting. Eric, Rod, Jason, and Tom, and we will see you guys all next time.